Let's do something new and fun. All right. Let me get the link for this. Share link. Copy. Okay. I think we are live and working. So I'm going to go over essentially, like, we're going to go over the pair, the factory, and the router from a data analyst point of view when I'm looking at Solidity code. Basically, like, what are the things that I look for? Just obviously, like, event and, like, function calls, right? Like, we already know those are what we're looking for. But normally, what's very important is, like, what's happening between those functions or what's happening before and after an event. And that's context you can only get from the reading the Solidity code itself, right? So I'm not saying like you have to know how to write Solidity and like you have to know like all the modifiers and like storage like optimizations and whatnot. But you do need to know start kind of how to read like how in Solidity are we calling other contracts? How is the ordering of these events kind of handled? Is there any data encoding happening? Yada yada yada. So that's all important. Usually you won't have docs to really look at, or the docs you look at will be completely terrible. In this case, normally where I would start is like, hold on. Let's do this on hard mode. Normally you have a GitHub, which is hopefully helpful. And I like to start with interfaces, right? So interfaces essentially is like the highest level, like what are all of the events and what are all of the functions within this contract, right? And this is just a very quick way of seeing like, all right, we have these functions here, which are all like your basic ERC20 functions. So like there's nothing, and same with these events, there's like nothing surprising here. And then you have these functions and events here, which are just like, all right, these are not normal ERC20 functions. These are probably the functions that I'm going to have to get into. Hopefully, most of the times, it's like obvious from the function name and like what's being returned, what the function is doing. Hopefully. So in this case, like the swap, like it's pretty clear in this case that like, okay, there's some amount coming in, there's some amount that's going out, and I actually don't know what the call data does here. So this would be something where I'm like, I do expect to swap out and in, but I don't know why there's an address, and I don't know why there's call data. Right, so that's like already like I would start writing down notes of like, okay, these are two things I need to look into, right? And something else that would be interesting is like, oh, why am I putting both how much I'm getting in and how much I'm getting out? Shouldn't it do the calculation for me, right? So this is something where I'm like, all right, that would be interesting. Something else you'll note is that these two code blocks are kind of separated, and you'll see that one of the main differences is these functions up here all have like view in them, or pure. Pure is like, how do I explain this? So functions have memory, like there's memory and then there's storage, right? So storage is like the contract is keeping track of how many tokens are held in the pair, and that's like a every time you want to access that or change that, that's a storage thing. But memory is like if I have a function that adds two numbers together, um, and I do like function input A, input B, and then it like has in memory like C equals A plus B, return C, then that C is a memory variable, right? So view functions can have memory, but they don't touch storage. Pure functions don't even touch memory. So um, that's always something good to know. So these are going to be like your read functions, the ones where we saw in the previous YouTube video of like, oh, there's a lot more traces calls than logs emitted, and that's just because um, it was probably one of these view functions called which don't emit logs, right? Versus these ones, which are actions that actions should always, for the love of God, should always emit events. Um, Otherwise, you just hate your data analysts and your front end engineers and your back end engineers. So yeah, we see there's mint, burn, swap, skim, sync. Swap is probably the easiest place to start. So I'm going to start there. You could either clone the repo and put into VS Code, but I think personally I'm fine with just finding the contract and just using def. I'm sure a lot of people have already seen me do this. .def.net. Sorry, .def.io. No? Code not found. Oh, I'm looking at the wrong thing. Hold on. Where's the pair? Where is the pair? This one. So we go to contract. And now we can do .def.net. And we have the pair. You'll see that there's this interface, which is the same one we were just looking at. And then we have this other interface. We have libraries. I won't cover libraries. And now we have... Hold on. So basically, all right, just to explain what's going on here. This pair contract is using a bunch of other contracts kind of within it for like logic or like inheritance purposes. So if you use deth, you're just going to see it all like what's called flattened. All right, if you ever see flattened mentioned in Solidity or whatnot, it's flattened is just like the file with everything in it. So deth gives you a flattened file unless it can make a cleaner folder structure. And I actually don't know when it does and doesn't, because sometimes deth makes a nice folder structure, but in this case, it's just a flattened contract. So I'm going to just scroll down to pair. Yeah, you can see we have the Uniswap factory in here, but we're not going to look at that. All right, finally, line 306, we've gotten to the pair. You can see it inherits the interface, and it inherits the ERC20 base Uniswap token contract, which I think is just like should just be like a carbon copy of OpenZeppelin's ERC20. If you haven't heard of OpenZeppelin before, please Google OpenZeppelin ERC20 API and read through this because you should know everything covered basically in these three, at least these two. Like you should have read all of ERC 721 and ERC20 on OpenZeppelin because it's just a great reference and they explain things very well. Anyways, so here, remember the what I was interested in earlier was looking at swap, right? So I'm just gonna scroll through, see if I can find swap. We can see mint and burn, which I don't really have to go into in this case. All right, we have swap here, right? So in this case, I can see there's a require. So, okay, so first things I'll check is usually the require, just because essentially it requires like if this require condition is not like satisfied, then you're gonna get a revert, right? So anytime you see a failed transaction and it says failed error because XYZ, it's like this is the code that's being emitted and this is the check that failed, right? So like this is important because some contracts or protocols have like a set of state management essentially. So like Aave v3, when we were looking at it last week, right? It had isolation mode, efficiency mode, basically like a bunch of different rules for like what you could borrow and use as collateral. And like that's something you would figure out kind of by looking at like the requires within like swap. Where in last week's case it was the requires within borrow, but in this case I can see swap. All it's checking is that like you're not swapping zero tokens and that there is enough liquidity in the pool for you to make this swap. Because yes, liquidity pools have minimums just so you're not like swapping out the very edges. It kind of goes to infinity, but I can see those are my two requirements. If I'm interested, sometimes I might be like, oh, this drives data questions for me of like how often does a pair hit insufficient liquidity, right? So I could do query for swaps where the swap failed and the liquidity was below the minimum, right? Obviously, the liquidity below the minimum is not data I can get from the failed function, but I can get the liquidity at the time of that swap, right? And kind of see like, okay, this pair hits minimum liquidity like X number of times a year, and this is how many failed swaps that causes. Oh, that probably correlates to when ETH is crashing like yesterday, and everyone's trying to run out of some trade, you know. So like this is what it's like. Okay, requires are useful for helping me frame more questions and events to look into. Require 2 does not equal token 0, 2 does not equal token 1. That's more of a so okay. So you're gonna have two types of checks, right? You're gonna have like logical checks where it's like you want to make sure that there's enough liquidity, and then you're gonna have security checks. In this case, it's just making sure that you're swapping the. Hold on, I need to figure out where 2 is going. Okay, this is going to get confusing because they have their own transfer functions. But basically, they're trying to make sure you don't transfer tokens to the wrong place. Because sometimes front ends will make errors, or users will make errors where they think like a parameter means one thing and it actually means another, especially when addresses are involved. People put all sorts of wrong addresses in. And like you don't want to get your tokens sent to a contract where there's no way of getting your tokens back out, because then those tokens are basically locked forever, and you've just basically screwed someone in the case that they swapped like 100K. It's like, oh shit, you can never get that 100K back. And in case you're wondering if that happens, yes, that happens. And there's like, someone honestly should create a leaderboard of like how much locked or lost liquidity of tokens there is of like ETH and USDC and whatnot, because it's in the millions. It's in like the tens of millions. So it's saying, all right, there's enough liquidity. You're not messing up the address. I'm going to try to transfer these tokens, right? And see if the transfer is kind of making through. And then they adjust the balances of the tokens in the pool, update, and then emit the swap event. Notice that the event is always emitted last, because normally you don't emit the event until everything has run successfully. But this is now when you start looking at like, all right, I know the basic logic here. What else is being called within this swap? And basically, you want to look for anything that has this pattern, underscore function with like brackets, right? Because those are internal calls. Basically, what is internal versus external? External is functions that can only be called from outside of the contract, or internal is functions that can only be called within the contract. So no one else can call update on the pair, right? Only functions on the contract can call this function, right? And that's like a security thing. So I see that the two internal functions in this case is there's an update function, there's a safe transfer function. This one's also important, but I'm going to come back to this later. So I'm just going to look for update. And I can see update is called within sync as well. All right, so here's update. Update is just saying, let me take the balances after the swap and update the price cumulative, essentially. Basically, you're moving the price curve, and then you're emitting a sync, right? So this is basically saying, all right, the prices, like the quantities of tokens in my pool has changed. I need to make sure that, like, the price variables that are red, right? Remember that price 0 cumulative, price 1 cumulative have their own read functions so that people can get the prices. I need to update these prices such that if someone else queries this contract, they're getting the most accurate prices and not the prices pre-swap, right? So this checks out with what we were looking at doing earlier, where for every single swap, there was a sync event, right? And now we know why. It's because swaps call sync every single time. And there might have even been more sync events because you could call sync without calling swap, right? There's also the skim function. I actually don't know how to explain this very well, but it's essentially a way of like arbitraging things to make. Oh, I should know this. Hold on. Let me not give a lazy answer. See the white paper. Skim. To protect against. Let me make this bigger. To protect against token implementations that can update the pair balance. Two bailout functions in the sync. Yeah, so sync is updating balances. Skim, in case enough tokens to overflow. Oh, okay. I wonder if, okay, it'd be interesting to see how often skim is called. But yeah, so overflow is error, not really error, feature of Solidity where like if you go over like the uint 112 max or whatever the uint size is max, then it overflows from the maximum back to 1. Or not to 1, to negative. Which is 1 in this case. Sorry, it does go back to 1. So skim would be there to make sure that if there's some excess, we don't overflow and someone can take the excess liquidity to keep things working smoothly. So yeah, like just from this alone, I can see like, okay, we were looking at just swap and like the emits of swap for trades, but if we actually look at the Solidity, you can already see like there's like 3 or 4 other things that would be interesting to look into, right? And like you can keep going down this path of like, okay, there's some interface being called where we're getting this, right? Like anytime you see like I something or some contract dot function call, this means we're calling some other contract. And the contract being called is this to address. Right, so like interface or any contract objects in Solidity, you have to say what address it is that this logic is being applied to. Then the contract's going to say, all right, I'm going to apply this ABI to this address and try to call this function, right? It doesn't know whether this function exists or not, but it's going to try to call it, right? So I can take this and try to find it. And I can see, okay, there's some function here, Uniswap v2 callee. It's only an interface here, so if I want this function, I need to go through here, and I need to find, hold on. And I need to find this callee. I don't see the actual function. Anyways, I'm not gonna waste time on that. I know we're already short on time. I'm gonna quickly go over the factory. So that's the pair, right? And then the pair, the main thing there was swap. I'm not going over mint and burn because I think that's more interesting to go through with the router. And I'm going to leave that as practice for you all, is go through this router contract and try to figure out how mint and burn on pair is used. I'm just going to quickly cover how the factory is used here. So, again, this is something you'll see me do a lot, but I'm going to have the factory open in GitHub in case I need to like pop around quickly. But I'm actually going to open it in Death. Not Death. Oh, not. And you're going to see the same thing, right? Where we have a flattened contract that imports every interface that we need, as well as any other logic that's useful. You can see the pairs in here, right? And you might be saying, oh, wait, why is Uniswap v2 pair in here? And we're going to cover that in a second. But we have... where's the faction? Hold on. Faction. Here it is. Line 394. You'll see there's a storing of every single pair in what's called a mapping. A mapping is basically like a Solidity JSON object or a Python or like a Python dictionary. You can see this is actually a nested mapping. So if I put in some address, then put in another address, then I would get the pair, if that makes sense. All right, so it's like the way to read this is be saying, I'm going to put in token 0 and I'm going to put in token 1, and it's going to give me the pair address if it exists. Right, and if it doesn't exist, it's going to give me 0x0000000. Right, so mappings is just a quick way of kind of storing maps from basically like, it's usually used for addresses, but like you'll remember that like emodes for Alpha v3 was stored in a mapping, right? Like user reserves or like user data is normally stored in a mapping. NFTs use mappings a lot. This is like probably the most flexible, most used data structure in Solidity, and the most annoying ones are where you have mappings of struct arrays. Anytime I see that, I get very upset. But in this case, this is simple. Again, this is just like a token search up, right? And you'll see that this mapping is actually used in oh, excuse me. A get function later, but we're going to come back to that. So there's a pair created event. We've already looked at this in question 3. If you haven't seen that YouTube video, it's recorded where we go over pair creations. So there's event for pair created, and then there's a function for calling create pair where you put in 2 token addresses and eventually it'll tell you where the pair is created. And again, first thing to look at, require. Always look at the requires, right? So this is a security require. It's not interesting for data purposes. It's just making sure you're not putting ETH and ETH in the same contract, because I actually don't know what would happen. It's making sure that you haven't put the 0 address in, because there can't be a token at the 0 address. And it's checking if the pair already exists, right? So this is the mapping that we were looking at earlier. And you can see they're putting in token 0 and token 1 and seeing if the address equals the 0 address. Because if it equals the 0 address, then that means there's no pair. And if it doesn't equal the 0 address, then that means the pair exists. This is a crate code. This has kind of changed a lot over the years. It used to be just like you would say like new pair equals new Uniswap v2 pair with like constructor perhaps. It used to be this, and then this would like return address of pair, and then like you would have this whole emitted thing, right? So essentially it's saying create a new pair, store this pair in our get pair mapping, put it into our all pairs array, and emit that the pair is created. And that was the create 0 opcode, but we now have a create 2 opcode, and one of the reasons that create 2 is nice is you can actually predict the address that the pair is going to be deployed to before it gets deployed. So it's like, this is useful for front-end purposes in case you don't want to wait for the contract to be deployed to check what the address is. You can get the address right away using create2 opcode. And you'll notice that there's this assembly bracket, and that's because when we're calling opcodes directly, you have to use assembly, essentially, right? And if you don't know what opcodes are, you should read Ethereum. Okay, you can either read the yellow paper, or you can just go to EVM codes, and EVM codes will explain to you every single opcode that exists on Ethereum, right? And you'll see create and create2 are both here, right? And they do functionally the same thing, but create2 allows you to put in a salt, which makes things predictable, is my naive way of explaining it. But that's assembly. Again, you'll only see this in assembly. More and more contracts are using assembly. Assembly is much harder to understand than Solidity. For example, the new Seaport contracts from OpenSea are all written in assembly. And once I understand that, then I'll do a session on it. But I'm going to be honest, I don't understand how to really read this yet when it gets to more than a few lines of assembly. So that's the factory created. I wouldn't say there's anything super interesting about it, like much less so than the pair. Like factories are just very, very standard at this point. There's some way of tracking them. You emit when a factory is created, and you check that there's no duplicates, and that's it. There are fees. I'm not going to get into fees. That gets complicated. I'm trying to think. Is there something I'm missing here? Yeah. Basically, assembly. This is an opcode. This is an opcode. This is an opcode. This is memory load. Right. This is adding. I think pair. What was it earlier? This is where my memory kind of fails me. I remember we were looking at pair earlier. There's something. Right. Swap had bytes call data. I should have done this earlier, but I don't know what that's for. Bytes call data. All right. Where is data used? Data is used only in this Uniswap v2 call, which there's an interface for, but I couldn't find. So typically if there's an interface, then the actual contract somewhere, and it's overriding the interface with the actual logic. And this is kind of bad practice, but typically interfaces will have a description above that explains like what are the variables being called and why and what they do, but Uniswap didn't put it in here, so we have no idea what this does. So if anyone from Uniswap is watching this, well, they do a good job of it in V3, so I can't be upset with them. Let's see if we can find it. A functional. Oh. Here we go. We're getting somewhere. It's commonly used for flash swap. Your contract that borrows from the pair needs to implement it. The exchange doesn't. Okay, so here we go. They do have docs on it. I just haven't actually seen this before. Developer resources. So flash swaps, flash lens, all of that's fairly complicated. I'm not going to explain it today because I actually can't explain it well, but I need to look into it. But this is a composability thing, right? So for most cases, if you're just exchanging on Uniswap normally, whether that's through the router, through 0x, 1inch, or whatnot, data is going to be length 0. And that's something we could check in the data. And like, actually, that should be something that I should leave us with. Is I want... I want the hashes from traces where Alright, what is the... Essentially, we want to check for swaps where data is not 0. So it's swap unit 256, unit 256. Oh, you know what? Hold on, there's a faster way to do this. In this case, go to Etherscan. This was the pair, and I just look for swap being called. Then I could see the method ID. All right, that's faster. We have this where, or actually in this case, we don't need to do this raw. We can do Ave, no. I kind of default to doing everything from raw data, but we should do pair call swap. Come on, doing search. Oh man, Uniswap's been forked so many times. It's so hard to find. Wait, is it not under this? Okay, hold on. Let's go to V2 engine. Because Uniswap should be in here. Uniswap's not in here? Okay. Uniswap pair swap. Select all from. That's probably too many. Let's do limit 10. So here I can see this is swap. There's amount 0, amount 1, data 2. I'm going to look for swaps where data length greater than 0. Okay. Greater than 2. One problem here is that... Okay, that did work. So there's a bunch of transactions here where the length was greater than 0. I was going to say this might not work because of, like, these Dune tables just look at where the to address is the contract, and it won't include traces. Oh, wait, no. Traces are included in here. Wait. Oh, that's new. Oh my god, that's amazing. Okay. I was going to say, one problem with Dune before was, like, traces weren't included in the function tables, but now it looks like it is. That's actually huge. Alright, so let's end on this. I'm going to take this transaction, and I can see that it's not even decodable, but there's some contract here that's also not decoded. So this is probably some bot, trading bot. And we're looking at potentially flash swaps being used, essentially, because that data is being transferred or passed along. And this would be something to kind of start looking into, of like, all right, what are the most common contracts built on top of the pairs that use data, and like, how can I understand how this data is being used for like flash swaps? That would be the next step. But yeah, again, that's stuff like you would only ever see this if you took the time to look at the solidity and ask like, what is this variable? And I don't know what it does. It's something you wouldn't figure out just being like kind of more naively just analyzing like the highest level um like basic swap or basic deposit stuff. I'm sure if we looked at Alpha V2, you would see stuff like that as well. Again, I did Uniswap V2 because I think it's one of the cleanest contracts to kind of look at, and they basically have like every single basic pattern you need to know, from factories to routers to ERC20 like tokens to like state management, and it's not overly complex yet. Like if you tried to do this with Balancer, you'd get lost, I would say. But try to run through this exercise yourself. Again, looking at the Uniswap V2 pair, the V2 factory, and the router. And like that's just good practice to get you ready to looking at like basically any other Solidity contract out there. And with that, I'm going to call it a day.